Welcome everyone, I am Akash and I will be presenting my topic, that is my project topic on analysis of GAN and its variants. So let's get started. First I will discuss about the generative models. So the goal we have here is that we have some training data that comes from the uh, probability P of data distribution, and then we have some fake data that that we want to generate, and that those generated examples we say that belongs to the P of model, and our goal here is to find P of model, or essentially we want to make our P of model very close to the P of data. So we want both the density functions to be very similar. So this can be done in two ways. The first is the explicit density estimation, and this we explicitly define and solve for the P of model, and we make some approximation in doing so. So it's not a very like accurate method. And other method is that we implicit density estimation. Here we try to learn a model that can sample from P of model without explicitly defining it. So here I will give you an overview. Like we have different types of methods available under generative models. Like we have some tractable density methods, which includes pixel RN and these things, and then we have variational autoencoders, Boltzmann machines, and on the right hand side we can see we have GANs. So these are generally distributed under two categories, explicit and implicit. So GANs falls under the implicit type, and we can also see that they belong to the maximum likelihood method, and that is also similar to the KL divergence, but GANs uses JS divergence. You will see that later. So GAN that stands for Generative Adversarial Networks. This is the framework of a GAN. Here we have two players. One is the generator, one is the adversarial. The goal of the goal of the generator is to generate fake images that are like real looking fake images, and the role of discriminator is to differentiate between the generated fake images and the real images. So generator tries to differentiate between the two types of distribution, and the goal of discrimination try to discriminate between the two distributions, and the goal of generator is to fool the discriminator. So here on the left side we take sample X from the data, and that sample then the differentiator uh, takes this sample X, and the D of X then tries to be near 1 for the real data. And on the right hand side we can see that we take a noise vector Z, that is our latent variable, uh, and we map this latent Z to X via a differentiable function G, that is X is equal to Z of Z, and then we pass it to the discriminator. Our discriminator takes the variable takes input Z of Z, and it tries to be near 0. So this is the goal of the discriminator, to be near 0 for the fake images and to be near 1 for the real data. And the goal of generator here is to fool the discriminator, that is by making D of Z near 1. So this is the objective function, minimax objective function for the generative adversarial network. Here we have expectation for sample X coming from P of data, uh, uh, log of D of X, and expectation of sample C coming from P of C, log of 1 minus D of Z of C. So the first term represents the data that is inputs that is coming from the real data, and the right terms depends on the fake data. So it is a two-player minimax game between the generator and discriminator. D tries to be near the local maximize the local likelihood, and it's like a binary classification problem. We want to classify want to make that real data as 1, and for the generated fake data we want to make it 0. And the goal of generator here is to minimize the log probability of its samples being classified as fake by the discriminator. So here we will see how the training proceeds. So first we try to maximize the objective function with respect to the parameters of the discriminator, and this is done by using gradient ascent on discriminator, and then we apply gradient descent on the generator. That is, we try to minimize this objective function with respect to theta of g, that is the parameter of the generator. So for the generator, the objective function, only the the right side of the function depends. So we only take the right side of the function that depends on g of c. We don't take this expectation of this. We don't use this part. We run this through a for loop, and we train alternatively. First we do a gradient descent on the discriminator, then we do gradient descent on generator, and then we again go to step 1 and 2. We repeat this process. So one more implementation detail here is that while doing the training, instead of doing the minimization of log of 1 minus t of theta d, what we do is that we remove that 1 and bring that minus 7 out, and instead of minimizing, we try to maximize it. The reason for that is that on the right hand side in this figure you can see that the blue curve represents the earlier version, that is log of 1 minus t of c of z. So the problem with this curve is that the curve is kind of flat near the beginning, which means that the gradient flow is quite low at the early stages of the training, which means the training will be very slow and there will be very less learning. And so we don't want this. In order to make the learning curve fast, we modify it to minus log of t of c, so that we have higher gradient flow coming in. Now I will talk about the base optimal discriminator. So we have our objective function here that is written, and then we try to write it in it using the formula of the expectation in the form of this integral in the second line. Then what we do is here is that we consider we try to kind of change the variable x equal to z of z, and then we use using the function of random variables, we write this in this form. So after doing that and doing some more modifications to it, and by taking gradient with respect to the discriminator, we can obtain the optimal base optimal discriminator, that is d star equal to p data of x divided by p data of x plus p of generator of x. So this is the optimal base optimal discriminator. So this is this is kind of a model which can be used to describe this. So here we have the z, that is our latent variable, and what we are doing is that mapping z to x, and these arrows represent the mapping. We are mapping z to x, and the dotted curve is the actual data distribution, that is p of data, while the green curve, that is the curve that we are estimating, that is p of model. So our goal here is to bring this p of model very similar to p of data, and we have the discriminator that is in blue dotted line. Discriminator tries to give us an idea about the closeness of both the models, p model and p of data. Suppose we make our p of data same as p of model, then you can see that our discriminator of x goes to half, that is 0.5. So in that case, this blue dotted line becomes 0.5 and it is a straight line, and at that point we will have our dotted data distribution coincide with the green model distribution. So that is the optimal discriminator. So now we'll see how our generator objective looks under the optimal discriminator. So what we do here is that we take our objective function for the generator, and we replace d with d star here. After replacing d with d star, you can see we have these terms in the logs, and then what we do is that we write it in form of KL divergence. We have two terms of KL divergence here. KL divergence is a term that is used to compare two model, like two density distribution, how close they are. So we have two terms here, and we have one more divergence, that is Jensen-Shannon divergence. So using that divergence, term can be combined in JST. So what we finally have is that when we are in optimality, we'll have our PG is equal to P data. At that point, this term will go to 0. And for more details, we need to look into the exact definition of the JST. When P is equal to P data, this will become P data, 2P data, and this 2 will cancel, and then we will have P data, and both of the terms will become P data, and they will be exactly same. So what will happen, JST will go to 0, and we will only have the term left will be minus log 4. So this is the optimal, this is what we get after doing the optimal, after taking optimal discriminator and generator. So this is our objective function, that is minus log 4 when PG is equal to P of data. Now moving on to some of the implementation details. Here what we do is that we run this algorithm in steps. First we update the parameters of the discriminator, and then we update the parameters of the generator. So how we do is that first we actually, it is not necessary that we train discriminator for exactly the same time as the generator. So we take some k steps. That k represents like k is a hyperparameter, and it is like the number of steps and number of times we are training the discriminator per one time we are training our generator. So we sample some noise samples m from the P of C, and we take some examples that are training example, and we then start our training for the discriminator. And then after this training is done for k steps, then we move on to the generator, and we again sample some noise samples, m noise samples, and then pass to the generator, and we run this in a loop for the number of iterations that we want. So the dataset, I have used two datasets here, that is MNIST and custom dataset that I created. So the MNIST dataset is like the consists of the 60,000 examples and 10,000 training test examples. So I will talk more about my custom phase dataset. So here this dataset is consists of faces of people, like people faces, and it has around 680 unlabeled face images of 5 people, and there are about like 135 images per person. I created this dataset by running a face detection algorithm on the normal photos and center cropping them. The images are then resized to 256 cross 256 resolution. So these are the two datasets that I used. So first I will show you my results for the GAN. So here on the left hand side, I've shown my model details. Like this is the model of fully connected neural network kind of model. So we have all the linear connections. So these are the model details. I will not go into that much. So here are the results that we have obtained during training. So here we can see that the orange curve represents the generator loss, and the blue one is the discriminator loss. So generator loss decreases over time, while the discriminator loss kind of increases during time. That shows that generator is learning to generate fake images, while the discriminator is kind of getting bad, but yeah, it's good. And here on the top right, I show some of the parameters that are used to quantify the results of the GANs. So here we have in this table, the first is the first parameter is the MMD, that is the maximum mean discrepancy. So it is a parameter that is based on the idea that two distributions are identical if and only if all their moments are same. So basically it gives us the similarity between two models. So it's better to have it lower, as low as possible. and these are the other types of metrics that are used to measure the parameters of GAN. So these are some qualitative results obtained till 200 epochs. So here I have shown the results after every 50 epochs. You can see it starts from a noise and is then is being converted into digits. The first, and finally we have some okayish kind of results for 200 epochs. There are several problems associated with GAN. So there exists a better model of GAN, that is the Wasserstein GAN. So it uses Wasserstein's distance, or what we call is the Earth-Morse distance, instead of the JS divergence that is used in the GANs. It provides a smoother representation of distance between the two distributions, and this is the definition for finding the Wasserstein distance. We will not go into the much of the details of this, but what Wasserstein distance takes two probability mass functions and computes the optimal mass that needs to be transported to make both distributions similar. The paper involves very complicated maths, and since the optimization of Wasserstein's distance turns out to be intractable, the authors solve the dual problem of Wasserstein distance, which is uh, Kantorovich-Rubinstein duality. The final formulations requires the function to be K-Lipschitz. So after all the mathematical part, what the main implementation detail here is that here compared to the standard gain we drop the log terms here and we directly take our discriminator, and we do not include our log term. So that is the main implementation detail that we have here. So these are the results from the WGAN experiments. So here is my model that is that is made out of fully connected neural networks, and then we have here on the right side as for some of the results like the previous GAN, and here these are the discriminator losses and generator losses. One notable thing is that the MMD, that is one of the very important parameter in quantifying the results of the WGAN, is that the MMD for WGAN is lesser than the MMD for the normal GAN, so that is good. Now moving on to the visual results. So first is the epoch 1 that only contains most of the noises, and as we progress with the number of epochs, we get to see some kind of digits. One more thing to note here is that these digits contains less noise as compared to that of normal GAN. Then just for the sake of implementation, I have tried to implement the DC GAN, that is deep convolution GAN. Instead of just using the fully connected neural network, here we use convolutional layers, and the architecture is pretty similar to GANs. Finally, I present some results of the DC GAN. So on my custom dataset. So first we have epoch 1, that is almost noise, and then we can see we can try to see that there is some kind of structure appearing out of the noise, and as we progress with time with the epochs, we can see there are faces that begin to appear. Two more interesting things that can be noted here is that the DC GAN network tries to learn some special features and their placements. For example, here I show two of them. That is, one is the bindi, that is you can see here in all those four images. The network has learned to place it correctly, specially. And the second is the mustache. Here you can see a female face but with a mustache. So the network has learned where to place the features correctly. So this is a good thing. So this brings us to the conclusions. So GANs can generate realistic looking images by using two-player incorporating minimax game, and it has many applications include like super resolution of images, image to image translation, and video frame prediction. But the problem here is that training GANs is very difficult. And one of the most common problem is model collapse. That is, our generator when our distribution is like Gaussian, our generator only generates images that are of similar type, and there is no variation in the types of result generated. So that is one of the problems. So other problems include vanishing gradients and lack of, yeah, one more important thing is that we don't have any proper evaluation metric for GANs. So then we have an improvement over GAN, that is WGAN, that attempts to stabilize the GAN training, but in doing so it tries to clip the weights. That still again causes instabilities. So it's better than GAN but still unstable. And then one more improvement that was done in WGAN is doing the gradient penalty that also stabilizes the GAN, but still it's an active area of research. The code will be released on this GitHub page. So these are the references I have used. Thank you.